Sir, we are live, sir. Sir, we are in live.
Hello all, welcome to Edumon Tutorials, and in this session we'll discuss about the important topics that are useful for the examination tomorrow. So as many of our students are writing the examination tomorrow for embedded system subject in 4th year first semester, so we shall have a glance of the syllabus and what are the important topics that are necessary for tomorrow's exam. Actually the syllabus has been reduced for 70%. Okay, so let us go with the screen for the syllabus first of all. Please share the screen with the syllabus. As you could see, this is the syllabus of embedded systems for the 4th year first semester. So where we have in the first chapter the introduction to embedded systems. So in the first chapter generally we study the basics of typical hardware, memory, microprocessors, buses, and then we have the topic called introduction to microcontrollers. So in this chapter we can expect the question from the 805 microcontroller and its architecture and the interrupt basics and shared data problem. So we see what are the important topics in 805 first of all. So typically discussing about an embedded system. So embedded system is nothing but a device or a small component which is embedded in another system which is controlling it there. So like we can take our examples like printers. Our daily usages are mainly washing machines, microwave ovens, okay, air conditioner systems and all these. So these machines actually are controlling the devices. So there are some design issues and the important aspects when compared to embedded systems. We consider them for designing these. Like the first one is compactness, because you are designing a machine which controls the other machine and it should be embedded in that. So the size of the machine which is going to be embedded in the system should be very small. So that is why you go with the microprocessors and microcontrollers. So, if for example, if you are controlling a AC machine with another machine which is the size of your laptop, that is not so feasible. That's not a good design actually. So we consider that this machine should be very compact in size. Next, it's response time. We know some applications which are working with remote control. So the access time should be very less and very accurate. For example, we take the example of automatic doors near our airports or hotels, etc. You can see the response time of the whenever the person enters before entering their into the airport or something, the door just opens automatically. So when the sensor sends the signal, or else the best example you can take is an airbag in a car, right? The airbag in a car should be opened whenever it senses some danger or else something is hit in the car. Immediately it should open the airbags. So here the response time should be very accurate. So these are some design issues we can come under this embedded systems. There are a lot many examples you can see in the textbook like printers, telegraph machines, etc. And how to design these machines. So basically we use small chips which are called as microprocessors or controllers. And so first of all you should know the difference between a processor and a controller. So these are topics which we cover across for short answers things like what is a microprocessor, also what is a controller, what is the difference between a processor and a controller, right? Yeah, so you can see the difference between a processor and a controller as we call the microprocessor as a simply as processor on a chip. On a chip, it is a small processor which contains control unit, arithmetic logic unit, and simply memory unit, and they're connected using an address bus, control bus, and data bus. So it can read the data and it can do some processing and give us the output. But it requires some peripheral devices like you might have studied in microprocessor subject about the peripheral devices like 8255, 8259, 8251, 8253, and 8279, which are used for providing timing, handling the interrupts, and the other possible operations for interfacing the other devices. But whereas coming to a microcontroller, we call this microcontroller as a true computer on a chip, because inbuilt it has the timers, counters, and interrupt controller, etc. So basically microcontroller has a limited space because if it contains all these peripheral device operations also, so it contains a limited amount of space. So it is used for only small programming rather than comparing with the applications of microprocessor. Microcontrollers are used for small applications, but it is very useful because we are creating these devices for embedded systems to do one particular task. Like for example, we are creating an embedded system for a microwave oven just for that bring the temperature and its timer. Right? It is intended to do a small job. So microcontrollers are always useful when designing a embedded systems applications, right? Embedded system applications. So we come across now what are the important things that can be discussed in the first chapter, that is 8051 microcontroller R. So you can see this is the architecture diagram. So this is the most important thing in the first chapter. So we can expect a simple question from any of the architecture we can see in this diagram. So it contains actually an arithmetic logic unit and registers A and B. So there's a small correction here. You can see this is a register A, which is called accumulator, and B register. This is program counter, data pointer, and we also have RAM and ROM. And in the RAM, we can see there are some special function registers which are given here in the diagram, right? Which are given here in the diagram, like IE, IP, PCON, SBUF, SCON, TCON, TMOD. So you can just remember the names of these, which are useful when you write an architecture. And internally, they also have these are the registers, which are also having 8 bits and explanation for each bit, uh, which is quite difficult to remember as of now because we don't have much time. So you can just remember what is the use of these registers actually. IE means interrupt enable, so which is used for when you are handling interrupts, and IP is interrupt priority. So interrupt priority, where we can assign some priorities for the interrupts when there are more number of interrupts, and so on. These are timer low, timer high, and all the other registers. You can just remember the full form and what is the functionality of that register, rather than understanding entire diagram of each register. It takes a lot of time. And coming to the main thing is DPTR. DPTR is the register which is 16-bit register in this 8051. This is the only 16-bit register which is used to hold the address, and that is what is connected to the ROM. You can see that 16-bit address bus is connected to the DPTR directly, right? And whereas A and B registers are 8-bit address, right? Now PSW is one more important thing, which is frequently asked question. Now program status word. PSW stands for program status word. So where in program status word it contains flags like zero flag, sign flag, parity flag, carry flag, etc. So we know how they are actually used, the importance of flags. So generally, even if it is asked about explain about PSW or a flag register, you can go with this answer. You explain each registers, and from the syllabus, again we'll go back to the syllabus. In this, you can see that microcontroller architecture and instruction set and programming. So basically, you can cover that architecture with the diagram, and one or two important topics from the architecture. The diagram is very important. And next, coming to the instruction set. So there are actually typically we have 255 instructions in 8051 microcontroller, and it's really hard to remember all of them, right? You don't remember all of them. Instead of that, you just remember what are the groups. Like you can see in this diagram. Right? In this diagram, you can see that 8051 microcontroller instruction set, right? Here they divided this instruction set into data transfer, arithmetic instructions, logical instructions, boolean instructions, and program branching. Right. So if you remember what are the data transfer instructions, we don't need to read all the 255 instructions, because again these can be divided basing on the addressing modes. That is one more important topic. So coming to the instruction set and programming, the two things you should remember are addressing modes and types of instructions. So in the types of instructions, you can go with data transfer first of all. So these are the data transfer, and sometimes arithmetic instructions are also like explain some arithmetic instructions. And the advantage of 8051 is you have a direct instruction to multiply and divide the values from the registers, which are unlike which are not available in the previous microprocessor what you might have studied, right? And similarly logical instructions. And mostly some important questions are like, what is the difference between the jump and call instructions, and how these jump instructions are going to work, and how actually these programming, when we're programming, how to go to the subroutines. So even if the question is asked like how to write the subroutines in 805 programming, we use these jump and call instructions to uh, write the programs with subroutines, right? So we'll go back to the main syllabus, which is from the textbook. I'd like to share the
Glitch. Wait for 2 minutes. Sir will be coming back.
So sorry for the small interruption here because of some issue sharing my screen. So this is the syllabus you can see in the textbook, which I'm sharing here, right? So in the first two chapters, you just read about the examples of the embedded system, typical hardware. So what are the hardware you're using, like sensors, microprocessors, and microcontrollers, etc., and the fundamentals. Here, the terminology of gates and all these are we already completed in digital logic design and different types of memories. And from memories, you can expect a question like, what are the different ROM variants? Like ROM variants are uh, PROM, EEPROM, flash memory, how they are actually programmed, and what are the erasable memories and all. So the main concept actually starts with your fourth chapter. So I wish we can take less time to just cover these basics. And in the first chapter, don't have much about these. Only important things are what is a microprocessor and the controller, which is not available in this textbook. And there are some resources that we provide at the end of this session. There are some lecture materials and all, which contains at 8051 notes. So you can go through that. So from the first chapter, these are only the basics. So the important thing which is in the syllabus is 805 microcontroller, right? And here, so from the next chapter, you can go with interrupts. So whether it is useful to allow an interrupt or not, first we discuss that. So many microcontroller applications or as the embedded system applications, there are always devices that are interrupting the system. So if you completely disable the interrupts, what happens is if there is a task which is priority having priority, that is not allowed any time sooner because the other less priority tasks are executing currently. So interrupts is always allowed. But when the interrupts are allowed, we can see that there are some interrupt basics here in this chapter, like what is the time taken and how to give the access to the interrupts. That is, when one process is running and the other process has interrupted the system, whether to attend to that system, that interrupt or not, that is should be decided by the microcontroller. So that is what we study in this. And the main important thing anyone is asking or any question regarding this embedded system is this 4.3, that is shared data problem. So without the shared data problem, you can never expect any question from the embedded system. So you can simply remember that uh, whoever is going to attend the exam, the shared data problem is very important. And because we again handle that problem in different architectures in the fifth chapter as well, in the fifth chapter as well, we can see that there are some different architectures. So how we handle the shared data problem there. So typically in this textbook, the shared data problem is discussed using this a small program which we call it as using a underground water tank monitoring system. So the example given there is to simply tell about that example. Assume that there is a nuclear plant underground which is having some important maybe a liquid or something. So it should be maintained at some room temperature or some temperature constantly. So if the temperature is changing, like for example, assume that we stored some important chemical underground, and if the temperature is not maintained correctly, that may explode or else that may leak, right? Like what they do in the nuclear plants. We have seen some examples in real time also, that we can see there are some leakage in the tanks and all. Recently in Visakhapatnam also we have seen that because of these leakages there are some poisonous gases that are out. So they maintain these tanks underground, and the temperature is always continuously monitored, so that if there is any difference in the temperature other than the expected one, there is an alarm that is going to ring, right? So here there is an example given. So basing on this one, here the thing is there is a temperature and it is always monitored continuously. If there is any change in the temperature, right, you can see here the alarm should ring, right? So a set of alarm. So if it is not equal, definitely this is going to ring there. So here the shared data problem is these two variables are shared with another uh, devices also, and if one of them is reading the value, maybe there is an interrupt that is occurred. We never knew that is an interrupt that is going to occur, because if there is an interrupt occurred between these two lines exclusively, you can see here in the while loop in these two lines, that is I time 0 and I time 1. If there is an interrupt occurred between these two, then the control goes to this interrupt, and it reads the values from other hardware devices. Actually, the interrupt before this line, item 0 reads the temperature from one variable, that is item temperatures of 0, and here if there interrupt occurs, the values will be changed, and then other values will be read into temp 1 but not in temp 0. So now there will be difference in these two temperatures, and this alarm will start ringing. But actually there is no issue, but here the alarm may ring because there is a shared data. This is what is a shared data problem. So to handle this one, this is actually called as a false alarming actually, right? So you can study some characteristics of this shared data bug here in the next topic, in the next page. Just understand what is going to happen and all. Then we come with the architectures in the next chapter, fifth chapter. So I want to discuss all this in a flash, so that when you read them, you can understand the important points and assume what is the question. Right. So coming to the fifth chapter, this is very important. And in the fifth chapter, we study about the software architectures. First one is round robin. So the example given here is, so most of them asking a question about how to understand this code, or else whether it is necessary to write this code or not. This is very simple. Round robin is very simple architecture where there are no shared data problem. There is no interrupts. You don't allow any interrupts. You simply think there are some AND devices. Like here you can see device A to device Z. They are given device A to device Z. So it will always check, simply the controller will always check if device A needs any service, right? If it is false, it goes to the next one, device B, and if it is false, it goes to the next one, device C, and so on up to device Z, and again it continues from the starting. So once the first device is been checked for either it wants any service, if it doesn't need at that point, it goes to B, it goes to C, and so on. For example, assume that after going to D, the device D, now the device A requires a service. It should wait until all the remaining N devices are completed this check, and it should come back. So here the waiting time of any device will be equal to the number of devices, right? Will be equal to its number of devices. The more number of devices you have in your embedded system, so the time, the waiting time will be increased, right? But this is very simple architecture, very simple to implement, because there is no problem at all in we don't need to worry about these interrupts, because we're not allowing any interrupts. There is no shared data problem, and so on. And the next one is round robin with interrupts. So what is the difference between the previous one and this one is, here we just allow the interrupt, so that any device, if it interrupts in between, it will the microcontroller will provide the service for that device. So here the code is little bit different here. So if at all any device gives an interrupt, you can see there is an interrupt handler for the devices A, B, and so on Z. So we add an interrupt routine in this one. So whenever the interrupt is there, the device will set its value true, function value of device equal to true, so that it gets executed. So you can see simply in this diagram, a small diagram, this is just a diagram which shows the differentiation between this round robin and the round robin with registers. So here in round robin you can see there is no priority at all. So from highest processing to low priority processing, there is nothing priority because everyone is same here. All are equal. Simply all are equal. And so this round robin is very simple to implement. Similarly, we can take the other examples. And my suggestion for those who are preparing for the exam is, once you read all these architectures, the next one is function to scheduling where we maintain a queue. The next one is RTOS, which is not discussed in this chapter, but in the later on chapters, like 8th chapter and all, we completely read about only the real-time operating system, which is very useful. So my suggestion in reading this one is there will be summary provided after the chapter, so which is shown here. I think you can see that I'm sharing my screen here, right? This summary. So once you're thorough with the summary, you'll be definitely sure that you don't do any mistakes or else you don't deviate from the topic, whatever it is asked. You can see round robin is very simple to ask. There are no priorities. So worst case time response time is sum of all task code, because if there are n, as we discussed, if there are n task codes, it will take the sum of all those. And here stability of response is poor because it should complete all of them and come to the starting again. But it is very simple. The simplest of all actors is very simple because the coding is very simple. So on, you can see all the four interests basing they are given basing on these attributes like priorities, worst case time, and always we are worried about the time complexity and the simplicity in implementing. So you can see real time operating system, that is in the last year the architecture. This is very good, having a very good response when there is a code changes, but it is very complex to implement. The coding is somewhat difficult compared to the round robin. So here most of the things most commonly asked question in embedded system is which architecture we need to choose when you are designing an embedded system. And here definitely the answer is it depends on your application actually, the number of devices you are having, the type of application you are using. So basing on that you can decide. For example, if you are sure that there will be definitely shared data problem, you should go to an architecture which is handling that better, right? So remember these four architectures are important, and you should definitely remember this table which shows the characteristics of all these architectures. And even in the next chapters also, the shared data problem is discussed and how it is actually handled in these four architectures, right? So again, next one is in this chapter, the as we discussed in sixth chapter onwards, we come with a real-time operating system, and here the important topics are like tasks and task states, right? So you can expect the question from this one, task and task states. So any task that is been running, it is a basic building block in a software for an RTOS. So it is very simple to write a task and it is running. It's like a subroutine when you write programs in your microcontroller or else even in a C program. It's like a small subroutine, and it will be possible in three different states. Either it is running state or ready state or blocker state. Running state is when when a task started to execute, right? When the microprocessor starts executing the task, we call that is running. And ready means when a task is ready. For example, some other task is currently being executed in the microprocessor, right? And another task is ready to execute. Then it will generally give a signal that it is ready to be executed. And blocked state, when a task will be going to blocked state is, for example, it is currently running and it needs another task to complete its execution so that it can complete that. Maybe it is waiting for the data that should be available, or else maybe it is waiting for some signal or some external event to happen, right? So then, for example, like an alarm should go, or else some some button should be pressed so that it should complete its task, or else some data should be uh, given from the another task. So these are the cases. So the task is not going to run any sooner. So to go into the blocked state. So we have the diagram to better understand this task and task states. Here you can see this diagram, right? When these tasks are going to run and when they are going to block. So this diagram is important. Please have a glance of this one. This is a really important diagram, and you can understand how the tasks are running, right? And next important concept is when there are many tasks, right? How they communicate actually. So how does it know whether it should get blocked or unblocked, right? And there is a scheduler here which will keep the track of all the task states. In which, for example, assume that there are n number of tasks, and so the scheduler is the one which keep track of the status of each task, whether they are running, they are in the blocked state or they are in the ready state, right? So there are some important concepts in this, and you really don't require these timing guidelines as of now. So coming to this data, when they, as we discussed, when there are more number of tasks and each of them have their own data, how can they communicate with each, or else how the data is transmitted from one of them to other? Like you can see individually, the task one has its own stack and the registers. So the data of task one is stored in this one, and this is the common data, right? This is the common data which is available. So how these communicate? That is what the next chapter is. Intertask communication systems, where we go with mailboxes, pipes, and queues. Right. Yeah, one important thing here we come across is uh, if you are possible to note down this one, right? You can go with the reentrancy. So what is a reentrancy means? If there is any task which can be called by many other tasks, right? Which is mutual to everyone, right? Those tasks are called as reentrancy code. The code which can be called from by many tasks is called as reentrancy code, right? So here we go with semaphores. The one important topic you can always expect a question from is the semaphore. So what is a semaphore is? Generally, it is like a signaling device which is used for understanding when you're handling these critical section problems, and of course the shared data problems. In this diagram, you can see a diagram of it, railway track and the engine. So this is a simple example of semaphore. You can see this first gate that has been closed, right? Once this engine is been in this region, right? This signals that no other thing can enter into this region, right? Assume this is the region one, and once this engine is going to pass to this one, it is still in this region. So you can see this one. This is still in off state, so that this engine cannot come into this region. So this is how a semaphore works. Semaphore will work like a signaling device so that it gives the other task, the remaining task, it will let us know that that is something is being executed in the critical section. So you need to wait and all, right? So here also you can see once this engine is passing this region, then this is enabled and this next one has entered into this section. So that is what clearly this example is given so that we can understand one task is in critical section and is being executed, right? The remaining task is going to wait, and once it completes and get back, right, it the next one can enter into the region, right? So there are also different uh, terminology we use here. We need to understand the terminology which is given in the bold letters here. You can see raise and lower. Raise and lower is it uses these signals like give and take, release, right? So some signals so that it is allowing other tasks to understand. If it is having, for example, it is having a access to the critical region, it will raise or else it will lower its signal. Like in Zoom classes now, you people have an access like you can raise your hand to ask some doubts, right? There is some question asked from the comment section about sorry about insulation. That you can see tomorrow. You can ask some doubts regarding the subject, not about the examination pattern, right? The examination pattern is same. Maybe the syllabus is reduced, but the examination pattern is same, right? So since the time is running, we have only 10 minutes left. So I simply discuss about the topics which are important in the next chapter. Instead of going to chapter wise, I just tell the important questions so that we can go through that. And always remember at the end of the chapter, you please go with the summary. That is always important. Yeah, coming to this one. Right. So in this seventh chapter, you can see the importance of timer functions and events and how interrupts are handled in Rtos environment. Those are the important topics. So how timer functions will be working, right? And next one is hard real-time scheduling. So when you're using the scheduling concepts, right? Hard real-time means we can see in the real-time applications, it is not always like expected. We might come across the unexpected events happening. So then we discuss about the how to handle them and saving memory space and saving power. It is always useful to write simpler programs because the memory is limited in microcontrollers if we are using them, and also power because we are not going to use big power resources to run these simple devices, right? So these are the important concepts you can come in the 8th chapter, right? And next one is we listed something here. Yeah, intertask communication methods, that is in message queues, mailboxes, and pipes. How these are used for in between the task to communicate with each other. Like we're assuming that there are different tasks they are running and they should communicate, not the people. They communicate, not the devices. The task should communicate with the other task. So they use that message queues, mailboxes, and pipes. And finally, how after developing this software, embedded system software, how can they be linked, right? So one device to other device. Okay, like it is we are embedding one device which is with other software into another system which is having entirely different devices and different configuration. So our aim is how they can be embedded into a target system. That is what we study in the ninth chapter. So the important concept there is what is a linker and a locator. And finally, debugging techniques. So before it's like testing your entire software. So you test it in the host machine, and you'll understand the importance of debugging. Because when there are bugs, before completely deploying into the machine, we'll be checking the bugs over there. So as of my concern, you can go through again. I'll come back to from the first chapter. I mean the first syllabus topic, or else I'll share you the syllabus copy. I guess you can see the syllabus copy again. Since the microcontroller topic is not given in the syllabus, I came across this one. So I'll just mention you the important topics here. In this first thing, only about the memories, different types of memories, 8051 architecture, instruction set, addressing modes, flags, and shared data problem. The remaining interrupt latency all will be gently for a short answers. And second chapter, you can see in the second chapter, it is regarding round robin with interrupts and difference between these four architectures. And the important thing is real-time operating system here and how to select. This is what I have shown you in the summary there. So once you're thorough with the summary of this fourth chapter, actually it is second chapter in the syllabus, but from your textbook it is fourth chapter. So don't miss that summary of that fourth chapter and how these tasks and task states are working. We have shown you some diagrams. And next important thing is semaphore. Semaphore variants, there are also semaphore variants like binary semaphore, mutex, etc. You can go through that. And so in the third chapter, you can go with the task state, and semaphores. And next, intertask communications, message queues, mailboxes, timer functions. These three are very important. So comparatively from the three chapters, you can attempt more than three essays, I guess. And the remaining, these are small topics. And of course, the last chapter I wrote is not there for the syllabus for this examination. So you can go with fourth chapter is very simple. You can simply consider about semaphores and saving memory and space. Right, semaphores, saving memory and space. And
Sir,
finally,
this is
last chapter you can
one
complete.
student. So we'll be getting 7 questions from 5 chapters.
Yeah, someone is asking question here. Seven. Yeah, in five chapters itself we have the 7 questions. I think the question pattern doesn't change. Even the last semester, those who attempted the examination, they might know that even if it is a 70% syllabus, the question paper will be same. The pattern will be same. You are going to attempt for 70 marks, where the first question is 2 marks, which is compulsory, and the remaining 7 questions you can attempt any 4. So as far as my concern, you can understand that the first 3 chapters are important because since there are only 5 chapters and you want to attempt 4 essays, you can easily guess that 1 to 3 chapters are covering the most of the syllabus in the textbook as well as in the syllabus also, right? So if you're thorough with this 1, 2, and 3 chapters, you'll be able to at least attempt the 4 essays because from 4 and 6 only, sorry, 4 and 5 chapters, you will be hardly getting 2 or 3 essay answers as far as my concern. But you can see the syllabus, most of the syllabus is in the third chapter. It is covering almost 2 chapters, and the second chapter is covering almost your fourth chapter in the textbook, right? So obviously that will be very useful. And in the first chapter also, half of the first chapter is not from your textbook. It is from 8051 microcontroller by Kenneth J. Ayala. Uh, at the end of this section, I think they'll be providing the materials and important notes in Edgemon tutorials. You can go through that, or else you can send a message in this website also, Edgemon website. So they'll be providing you with this materials and all. So in this short time, those who want to really get through this one, want to attempt more number of questions and get good marks, I thoroughly first go with these 1, 2, and 3 chapters, definitely, right? And mostly second chapter is only one chapter from your textbook, but 1 and 3 are at least 3 or 4 chapters, right? But you cannot go to the third chapter without understanding the second chapter. So you continue your study with 1, 2, and 3 in the same order. Once you complete your thorough, very good, very much thorough with these three, then you go with the fourth one because most of the syllabus is covered in this 1, 2, 3 chapters. And some other guys having the question like most marks weightage. Yeah, that is what we discussed. Most marks weightage is as far as I think it is from the first chapter and the third chapter. Because in the first chapter itself, there is an introduction to microcontroller architecture and instruction set program. That is a huge chapter in your second year microprocessor subject. That itself is a chapter. That itself is a textbook. So maybe you may get 1.5 questions from the first chapter itself, and in the third chapter also. So maybe from 1 to 3 you'll get at least 4 essays. Because from 4 and 5, however, you don't have the sixth chapter which is IoT, right? From 4 and 5 hardly you get two. So the remaining 4 or 5 essays will be from 1 to 3 chapters, right? And most important thing is Rtos. And after reading every chapter, I wish that you remember the summary, right? And diagrams. Coming to embedded systems subject, obviously diagrams are very important. Either architecture diagrams, like task states diagrams, and some examples for semaphores, right? And there are some sample codes. You don't need to write the entire code. If you understand the first three lines of the code, you can easily write the sample code in round robin, even in the shared data problem. The most important topics are 8051, shared data problem, the architectures, and the tasks. That is it, right? So, any other doubts in this online session, you can ask now, or else maybe later in the Edgemon website or in the app you are having that. And I wish the admins will be providing the notes, right? The
Yes, sir.
admins will
Yes,
be
sir.
providing notes and
Yes, sir. Yes, sir.
all the best for all the any doubt.
There's a doubt that any important questions, sir.
Yeah, just now I've been expressing all that, right? 805 and microcontroller architecture, addressing modes, and instruction set. So I also told instructions that you cannot read all the 255 instructions. So read it like what I'm showing, the different types, okay, the categories like data transfer, arithmetic, etc. Okay, so that it will be useful. And remaining from the architecture and different architectures, and in that RTOS is very important. The next one is tasks, how the task is working and the task states, and definitely shared data problem, because the shared data problem is existing in different chapters. In the first chapter they discuss only the problem. In the next chapter they discuss how it is handled in different architectures, and in the third chapter they discuss again how RTO is handling the shared data problem. So without shared data problem, I don't guess you are going to see a question paper tomorrow. Right, that is definitely important.
So there's other question. So what about fifth chapter?
Yeah, what about fifth chapter? Fifth chapter is okay, from the textbook. It is actually I think eighth and ninth chapters. You can see how a linker or locator is used for embedded software, right? And next one is testing your host machine, right? Because that's a very small topic actually. The only thing is after developing how you are going to put it in the target system and how you are going to test it. Those are the two possible questions here, right? Because there are a lot many debugging tools. I wish that you can complete the syllabus 1 to 3 thoroughly first of all, because you're very much thorough with 1 to 3. I think you wanted to go to fifth one also. It takes a lot of time for 1 to 3 basically. You can see from the textbook also they cover up to the seventh chapter, right? So any more questions you can ask here, or else we can log into that website at Jimon and can put the comments there. And
So there's other question, sir. For task communication, should we write those long programs?
should we write those okay long programs in the sense? See, when shared data problem is asked, you can just explain the problem which I have showed, right? Which I have shown with uh, the problem where actually it existing. Okay, then you can explain your own words whatever the remaining different ways they implement it. Even if you are really try to read the code, you can understand that they write for if the device A, device B, and so on up to device Z. Right? You can take an example 2 or 3. No need to take n devices, right? And interrupts also. If you clearly understand the code, that is actually 3 lines of code which is repeating for all the devices. So that way, that's why it looks so big. But actually, if you understand the concept, that there will be 3 lines of code for interrupt and in the main program, and that is repeated for all the devices like device A, device B, and so on up to device Z. So it looks a big program. So I don't guess you need to write that much of program, but you can simply write a piece of code, at least a piece of code, so that you can explain actually where the shared data problem is or how it is actually uh, handled in that architecture. But huge progress is not necessary. Even in any type of examination, we are not going to write huge programs. For example, if you write data structure, they're not going to ask the entire lab program, right? They just ask you a concept like in a linked list how to delete, just the main logic part. So that is what useful here. But basically, you cannot skip anything in the diagrams, like task state diagrams, architecture diagrams. In diagrams, you cannot, skip some points, but program, you can write the main logic on it, based on the question asked. Right. So, okay, thank you all. So, wish you all the best for the tomorrow's exam. And
Thank you so much
please,
for speaking, sir. So
okay.
doubts are everyone
So
clear,
please
sir?
maintain the social distancing, and I think you know the rules of those who attempted in the last class also, right? I mean, last time examinations, how you have attempted, is make sure that you maintain for same guidelines because you know the
So
situation
there's
outside.
one
But
more doubt here actually.
yeah,
Will you explain about interrupt routines in real-time operating system?
in the real-time operating system, okay, I'll again share the textbook now.
So the
Are you getting that? I mean, the system. I
no,
stop
sir,
the
only
screen
syllabus.
share.
Yeah, I
Yeah,
cannot see.
I'll share the again. I'll share the window. That will be better, I guess.
Yes, yes.
Right? Are you able to see that now?
No, yes, no.
So there are some questions arised before design, like some design issues. Please remember the design issues also when you handle these concepts. What are the three important rules, or else there are some rules which are to be followed. Maybe they'll be asked for small answers because we are not concentrated much about the short answers here, right? We are discussing about the essay questions. Yeah, here. So these are the two rules, very important rules when you try to attempt implement an interrupt routines, right? So first thing is an interrupt routine must not call any RTOS function that might block the caller, right? So there are some functions which might block the caller. So we should be able to understand which are the functions. So clearly, RTOS is real time. In real time, we'll be guessing that some functions will be blocked, right? So a routine must not call any RTOS function, right? That might block the caller, right? Because once it, for example, if a task is calling another function and it gets blocked, it gets blocked infinitely because it is waiting for some event to occur, right? Right. And the next question is an interrupt routine may not call any RTOS function that might cause the RTOS to switch task, right? And because without even RTOS knowing what is the purpose of the task, right? It should know whether it is a task that is going to execute or else it is a blocked one. I think there is a small program over here, right? So to provide these two rules, we have here first one is no blocking, right? We call this as no blocking, right? So where it will not allow anyone to block that first interrupt routine. I think you know what is meant by interrupts, right? And there is also some concept called nested interrupts, which is asked for mostly for 2 marks, right? A program is calling another interrupt. There is one more question now. How complex can we expect a shared data program? Okay, shared data program. So when there are nested interrupt routines, it is more complex, right? Because when the interrupts are go on calling another interrupt routines, okay, a main program calls a subroutine, and that subroutine again interrupts another thing. And when the interrupt is being handled, ISR, we simply call it as ISR, interrupt service routine. That is very important. If the ISR has occurred and the microcontroller switches on basing on the priority to that, and again another ISR interrupts, it should be able to decide when there are multiple number of interrupts that are waiting for the uh, execution. The RTOs really need to understand the priority, and sometimes some tasks will be infinitely blocked. So to avoid that, right, the second rule is maintained here. No RTOs calls without fair warning. So simply it says that if you the process is this is the thing, then it might get blocked, right? Generally, we uh, also do some softwares and we go through some websites, we get a warning sign so that if you continue in this process, there may lead to some kind of uh, interruption or as mismatch over there. So you can see here in this diagram they will show that, right? When a lower task has been executed here, right, and an interrupt service routine has been occurred, right? So since the task is low, definitely the microcontroller will go to this ISR, right? Right, and the task will be communicating using these mailboxes or message queues, whatever, right? It will be sending with Rtos and all. You can see the message passing between them. Once it is completed, right, we should be understanding that is whether it's going to the next higher task or the task which is having the low priority. If there is any higher task waiting, for example, while executing this ISR, if there is any other task that is having higher priority has uh, encountered its signal, then it should decide whether to go to this one or the next one. Yeah, regarding shared data problem, how complex can we expect it? The complexity is not like one thing is, first of all, if you're asked to only explain shared data problem, right? You just explain what is the shared data problem. You don't need to provide any solutions. And there are different ways that is being provided a solution. One solution is they simply disable the interrupt between those two lines. We told you that. I'll go back to that. It clearly explained that where the problem is in the shared data problem. There may be a chance of shared data problem if the interrupt occurs between those two lines of code. And for example, if you enable and disable the interrupts between those two lines, so you don't allow any interrupt to occur between those two lines, you never have a shared data problem. That is one of the solution that is provided, right? I think you'll see that in the fourth chapter here. Yeah, after disabling interrupts. Disabling interrupts is okay, but not always because a higher task will be waiting. Yes, we use it that here. Yeah, this one. I think you can see the screen here. If there is an interrupt between these two lines in the while loop, right? Then there is a chance of uh, shared data problem. So to avoid this one solution that is provided immediately is just disabling the interrupts, right? You can see here in this code, it's simply disabled. Disable indicates this functional disable interrupts, so that between these two lines we don't get any interrupt, and after these two lines again it is enabled, right? So whenever if there is an interrupt, there is no chance of interrupt occurrence between these two lines. This is simply how they handle the interrupts, right? The same code is explained again in assembly language code, which we are not at all familiar with, generally speaking. Assembly language codes, right? So the same thing here, DI and EI indicates disable interrupt and enable interrupt. So between these two lines, we shouldn't allow an interrupt to occur, right? So that is what they did here. So this simply solves the shared data problem with the concept of disabling interrupts. So if you're asked like explain shared data problem and how it is handled using the interrupts, I mean disabling of interrupts, you can just read these two parts of code. One code for how what is a shared data problem, and the other code, the same code you write, you just add these two lines, disable and enable, right, between those lines. So that is the problem. This is the solution. So you might feel like if you read it individually, you might feel that this code is difficult. But if you understand what is shared data problem, always for any chapter, for anywhere, any architecture, the shared data problem is common, but it depends on how you handle it. And sometimes one way is because it is not for following that atomicity. That is, I think you know atomicity is what you studied in your DBMS, all or nothing property. Either it should get executed completely or nothing should be done. So in this while loop, that looping structure should be atomic. So either it should complete, it should be executed completely or nothing should happen. Because of some non-atomic, the shared data problem is occurring here. Okay, there is a link provided here by the Edgemon admins, so you can find some materials and notes in that which is useful for your examination preparation. Right. I think you are done with this. So almost completed almost 1 hour. So most of the students will be having a very less time. So I wish you all the best for tomorrow's exam. So please maintain all the guidelines and maintain good social distance and write the exam well. Thank you all.
Thank you so much, sir, for spending your valuable time and spending the time with us. Thank you so much for being here, sir. Hope all the juniors write and score well and revise all the important topics said by sir and share it with your friends who must be watching YouTube today to score well in exams. So thank you, everyone. Thank you so much, sir.
Yeah, thank you all.